Hi students, welcome to preliminary chemistry and the water topic, and this is video number 14 on saturated solutions. We looked in the last video at how we can build models and try and track what's going on with ions in solution, and hopefully this video will help you to fill in just a couple of those little gaps to follow on from those radioactive traces and how we use those. And also, I guess more importantly, to just fill in a few of these important terms that we often use when we're describing solutions. And one of the most important of those is the saturated solution. So a saturated solution is a solution in which no more solute will dissolve in the solvent. Once a solution is saturated, any further additions of solute will be deposited as a precipitate on the bottom of the solution, or depending on the substance involved, it may remain as a suspension within the solution. One of the important things that I talked about before was when we had potassium ions and iodide ions in solution, and we were trying to track what happens with radioactive traces. So what would happen if one of these was radioactive? Now the important thing about this is that whilst these may be in solution and while they may be leading towards the formation of a solid precipitate, for example, PbI2, what we do notice is that when we start tracking ions in solution, we do find that even if we start with a saturated solution and we add some lead ions, lead iodide to that solution, we know that it won't dissolve because we've reached the saturation point. But what we find with these radioactive traces is the traces are actually shifting around in terms of their position. What this means is that we need a slightly different model for trying to explain what happens in saturated solutions. So hopefully the one on the next slide will help. Our model is that saturation is a dynamic process. So once a solution has reached saturation, we set up what is called an equilibrium. Now, an equilibrium is a very important chemical concept, and it's a dynamic process. What it effectively means is where we have a reaction occurring in the forward direction, there will be a point where the reverse reaction is occurring at exactly the same rate. What this means is that we don't observe any changes at the macro level, at the big level where we can observe color change, formation of gases, the formation of precipitates. We don't see any changes. It doesn't look like there's becoming more precipitate or less precipitate or more gases or anything like that, or changes in the color of the solution. But at a micro level, things are still happening. The rate of ions that are being added to the solution, that is, from the precipitate, if we look at a solution here, from the precipitate that's following these red arrows going out, is from ions from within the solid becoming ions of solution. And that's happening at the same rate as the black arrows. So as these ions in solution are precipitating with other ions to form the solid. Forward and reverse processes occurring at the same rate. If we continue with our example that we've used in the last two videos, that is iodine and lead form, and with it, instead of a single headed arrow, a double headed arrow to the lead iodide solid. Now, because this has low solubility, then the number of ions will be small and the amount of solid will be large. Proportionately, equilibrium does not mean equal amounts, it means equal rates. So the rates of reaction are equal. And this makes it much easier for us to understand these processes and how they are occurring. So effectively, what we say is at the saturation point, the rate at which the rate at which lead ions and iodide ions are forming lead iodide solid is equal to the rate at which lead iodide solid is producing lead ions and iodide ions. So what this gives us then is a couple of important things to remember about any precipitation reaction. The first important point is that the precipitate will only form if the quantity of solute is greater than its solubility for a given volume of solvent. So let's pick something like potassium nitrate. Potassium nitrate has a solubility of 38 grams per 100 mils. That is, if we have 100 mils of water, we can add 38 grams of potassium nitrate before a precipitate will dissolve. If we add 37 grams, there will be no precipitate. If we had 39 grams, there will be 38 grams of potassium nitrate in solution and 1 gram, which will be a precipitate on the bottom. But that 1 gram will remain 1 gram, but the actual ions will constantly be shifting and changing. And that's because precipitation is a dynamic equilibrium. The rate of the forward reaction equals the rate of the reverse reaction. And just to practice that, if we were to represent the one that I just gave you then, that means the rate of potassium ions and nitrate ions forming potassium nitrate solid will be equal to the rate at which potassium nitrate solid is forming potassium ions and nitrate ions. And this is how we represent our ions in solution when they're in equilibrium with the precipitates. And it's probably a good idea too to just remember all of these are in aqueous solution, so the ions have the subscripts AQ. Thanks for watching.